what are the steps over here? So let's go through the steps. So here we are doing this in parallel. So as I said that these numbers are small, so therefore I can do this division in NC1. Here I am again computing a iterated addition, that is in NC1. Okay. Here I have already computed the table of the discrete logarithm. So here I am using the anti-logarithm table. Okay. So given yi, I am computing what is the power ai such that yi is congruent to g to the power ai. Okay. And here I am doing the opposite one, given a, I am computing what g to the power a is. Okay. I am setting that as t, and that is it. So what next? So next we will show is that, so what we have now is that we can compute iterated product modulo a prime power. Next we will show is that how we can actually represent our actual product as a product of, so how we can represent the actual iterated product as an iterated product modulo a prime power. Okay, how we can actually come to that. So for that, what we will need is the okay, so before getting to that, let me just state one more exercise for you, or let me state it as a theorem and you can actually verify the details as a exercise. So this is something that is not difficult to see. So given x and y to n bit integers and m which is less than or equal to m, computing x to the power y mod m is in log uniform NC1. The proof idea is actually just a few things, but I will just give you some hints to the proof. So what we do is that instead of x, first what we will compute is x mod m. Okay. So first observation is that x to the power y mod m is the same as x bar to the power y mod m, where x bar is equal to x mod m. This we can compute, right? We have seen last class that given a number x and a small number m, I can compute this efficiently. Okay, so I can get x bar efficiently. This is an exercise for you to check. Actually, this is not even an exercise, this is actually quite obvious that x to the power y mod m is equal to x bar y mod m. So we have reduced x to x bar. How can we reduce y? So instead of computing with respect to a large power, can you say that I can write again? So this is point number 1. Point number 2, can you say that x bar to the power y mod m is the same as x bar to some y bar mod m for some y? Can you guess what that y bar should be? Exactly. So it will be the size of that multiplicative group mod m. So the size of that multiplicative group we have already seen. What is it? So it actually basically, well, we haven't seen the size, so it is basically all the numbers that are co-prime to m, right? So I can write this as y mod phi m where phi m is number of elements in Z mod mz that are co-prime to M. Okay. So verify this. So 1 and 2, please make sure you verify. 1 is very easy, 2 is a little bit more work, but it is also an easy exercise in group theory. And once you have verified this, essentially what the problem boils down to now is computing x bar to the power y bar, where both these numbers are very. So again, observe that phi m is even smaller than m, right? So I am computing a small number to the power another small number mod m, and this actually can even be done by brute force. Okay. So this is easy to do. Okay. So now let's move to the next result.
Y bar is still of the order of n. No.
It is of the order n. Yeah, it is actually less than n. Yes. Y bar is less than n. So it has log n bits only now. Y had n bits. So y bar is equal to, is at most phi m is at most m is at most n. Yeah, yeah, you have to do repeated squaring, which is fine because the numbers are small now. So yeah, by brute force I meant repeated squaring only. So think about it. Okay, actually that is also not very obvious. It is not immediate. So that is also an exercise. How you can do it, how you can give a NC1 circuit for this now. Okay. Yeah, so I don't think we will be using this result, but this is just, as I said, interesting to observe. Okay. So now, okay, before I give the definition, I have to state the problem. So how do I want to state? Okay, just call it the Chinese remaindering problem. Okay. So what is the problem? So given C1, C2 up to Cn, where each of them are less than n square and pairwise co-prime, and x1 up to xn such that xi is less than ci, compute x such that x is between 0 and product of the CIs and okay, and for all I, x mod Ci is equal to xi. So let's try to understand this. So what this problem says is that if we are given a set of numbers that are small in the sense that they are bounded by n square and they are pairwise co-prime. So for any ij, Ci, Cj are the GCD of Ci and Cj is equal to 1. Okay, so they are pairwise co-prime. And you are also given another set of n integers such that each xi is at most Ci. Of course, they are, you can assume they are greater than Ci. Yeah. And okay, let's assume it is strictly less than Ci. I mean, I don't think it matters, but okay. Now, given these two set of numbers, we have to compute a number x, okay, such that x is not too large, okay, x is at most the product of these Ci's, and x has the property that if I divide x with Ci, the remainder is equal to xi. Okay. This should be true for all I. So now the first question is, so what is the first question when one sees a problem like this? That why, I mean, should such an x even exist, or why should such an x exist? Okay. So this brings us to the Chinese remainder theorem. So there is this again a theorem by the same name, which says that if you are given these Ci's and these Xi's which satisfy this property, then there exists a unique x, okay, so there exists an x which is less than this product, and that is the only x which has this property such that x mod Ci is equal to xi. Okay. And the theorem is again not very difficult, so you can try. So existence, uniqueness is I think quite easy to prove. Okay, so if you assume there are two such numbers x and y which have this property, you can very easily show that x will be equal to y. Existence is again a little bit more difficult, but it is again very elementary linear algebra. Okay, so using some not linear algebra, but yeah, elementary algebra. So using some elementary algebra, you can show that there exists such an x. So you can actually try proving this by yourself if you are interested, or you can even look up a proof. It is there everywhere. Okay. There exists a unique such x always. Okay. So this is the Chinese remainder theorem. Okay. So I leave this as a exercise for you. But here we will assume that this is true, and our task is to compute this x. Okay. So what we will show is that, well, we may not always be able to, so at this point we might not be able to compute it, but we can actually reduce it to one other problem. So what we will show is the Chinese remaindering problem is NC1 reducible to the problem of computing these product of Ci's. So basically, if someone gives me this product as an oracle, if someone tells me what this product is, the rest I can do it in NC1. Okay, that is basically given all these xi's and all these ci's, I can output an x such that x mod ci is equal to xi. So the proof is somewhat similar to what we saw earlier. So again we will basically be operating in this multiplicative ring. So okay, so what we do is first we are given all these ci's. So first we compute the product of ci, so let's call it as c, using my oracle. So this is the only step where I will be using this oracle. Now once I have computed c, the rest is just all NC1 computation. So set Vi as equal to C by Ci. Okay. So what is Vi now? So Vi is basically the product of all the Cj's other than I. Okay. So in other words, therefore, for all j not equal to I, Cj divides Vi and Ci does not divide Vi. Why can we say that Ci does not divide Vi? Cj divides Vi is clear because C is the product of all the other Cj's. Okay, so they must be dividing this. But why can I say that Ci does not divide Vi now? Because because by our initial assumption that all the Ci's are co-prime. So none of the other Cj's has Ci as a factor. Okay. Huh? Why?
Why does not divide
Uh,
Vi?
why Cj divides Vi? Cj divides Vi because that is how it is defined, right? C is the product of all the Ci's, right? So it must divide. So for now, if I take j to be anything other than I, it must divide, right? And because I have, okay. Now we will compute Wi, which is Vi inverse mod Ci. Okay. So this again, Ci is small for us. Ci is bounded by n square. So this we know how to do it in NC1. We have seen last time. What can we say about this quantity? So what we can say here is that, well, Wi is greater than 0 because it's a remainder, and it is less than Ci, right? And because Wi is equal to Vi inverse mod Ci, Vi Wi is congruent to 1 mod Ci, right? What else can I say over here? I think that's okay for now. I think it's okay, and let us just set this quantity as Ui. Okay, so this product I'll just call it as Ui. Now next step is, so again before going into the next step, what is the value of ui? Okay, so what is a bound on ui? So note that ui, which is equal to vi wi, so vi is nothing but c by ci, okay, and wi is at most ci, okay. So this quantity is, I can write this as at most this, so this is actually at most c, okay. So each ui is bounded by c for us. So next, okay, that's fine. We compute sigma, let's use j xj, let's give this a name. Y equal to xj uj. Okay. So what can we say about y over here? Now y mod ci is equal to sigma xj uj mod ci. Vj wj mod ci. Now what can you say about this sum? What are all the terms? Okay, so here, I mean, purposefully I have used a different index j over here because I is the one which is with respect to which I am taking the modulus, and I have all these terms over here. So look at all the terms when j equal to 1, j equal to 2 and so on. What happens when I divide it by ci? Okay. So what is vi over here? Okay, so look at this term vi's. Okay, so I have all these vj's over here. So when j is not equal to I, okay, so for every j that is not equal to I, Cj divides Vi, okay. So what will happen to all those terms? What will happen to the remainder modulo all those terms? They will all be 0, okay. So because Ci for all j not equal to I, it divides Vj, therefore this is equal to 0. So which is the only term that remains? When j equal to I, and what happens when j equal to I? So when j equal to I will have, well, this will be equal to whatever. So VIWI is congruent to VIWI is congruent to 1. So this will be just Xi mod Ci, right? And that's it. In fact, I don't even have to write this mod over here because I know that all these Xi's are at most Ci, right? So Xi mod Ci is the same as Xi. Okay. Okay, so I don't even need to write this mod over here. So now what we do is that one more observation. What is the bound on this value? Okay. So y is of course greater than z. What is an upper bound on y? So how many terms are here? There are n terms in this summation. What is the value of each term? So each of these xj's are bounded by Ci. Each of these Ci is bounded by n square. So I have n times n square, and each of the uj's we have proved it is bounded by C, right? Each of the ui's are bounded by C. So it is n cube times C. Now what we do is that in parallel for all t equal to 0 up to n cube minus 1, compute y minus tc and output x as y minus tc such that y minus tc is greater than 0 and less than c. Okay. So y is bounded by this, so I have to go at most till the value of t equal to n cube. Well, okay, n cube, I can go up to n cube also, doesn't matter. I'll have to go at most till the value of t equal to n cube before it becomes negative, and I'll check for each of those values of 2 when is y minus tc between 0 and c, okay. And that is my value of x that I want to output. And we have just shown that if I output this as the value of x, it will satisfy my given criteria. Okay. So why is this? So okay, maybe I can just write this over here. So again, note y minus tc, if I do mod ci, what is this equal to? So all these ci's are product of C is basically the product of all the Ci's. So doing modulo Ci, this disappears. So this is just congruent, in fact equal to y mod Ci, and here I have proven that y mod Ci is equal to xi. Okay. So the number x that I am outputting at the end has this desired property. Sorry, not Ci, xi. Okay, so we are all, which one?
Why it is less? Why is the upper bound n cube?
So this is my y.
So it is.
There are n terms. So I have an n over here. Each xj is bounded by. So each xj is bounded by cj, and each cj is bounded by n square. So that is therefore each x, So each xj is bounded by n square. So therefore I have the n square. Now each uj, we have shown it is bounded by c. So therefore it is n cube times c. In fact, yeah, I can have n cube minus 1 because it is actually strictly bounded by n cube times c. Okay, this is a strict inequality. So it is strictly less than that. So, but it's okay. Okay, so we are almost there, just maybe a little bit more is remaining to complete the proof. We need one more important tool that we will be seeing next time. It is what is called a good modular sequence, and once we use that tool, we will be able to get our actual problem, that is division in NC1. Okay. So, I will stop here today, we will continue next time.